Hello guys, so welcome back to this channel. In today's video I'll be teaching you guys Gauss Law, which is a particular topic in Phys 102. Okay, so please stick to the end of this video because I'll be teaching you guys a lot of important things in your Phys 102. Okay, so now let's start with the very first part of this class. Remember, this class is divided into 4 parts. Okay, the first part we talk about electric flows. Okay, the second part we talk about Gauss law. The third part we talk about application of Gauss law. Then last part we do questions and answers. Okay, so now let's start with the very first part of of this class, which is electric flows. Okay, electric flows. Now you may ask, what is electric flows? Okay, it is very easy. Okay, so electric flows, it has this is symbol. Okay, so this is symbol for electric flows. Okay, so electric flows is the product of electric field, is the product of electric field passing through a given area. Okay, so this is electric flows. Okay, so what is electric flows? Electric flows is what? Electric flows is the product of electric field passing through a given area. And before then, please, if you have not gone through our previous class on electric field, electrostatic and the rest, please, I will advise you to do so. Okay, so now let's continue. Electric flows is what? Is the product of electric field. Remember, this is electric field, right? So it's the product of electric field passing through a given area. Okay, now let's dive deeper. Okay, now there are different categories that explain electric flows. Okay, so this is the formula for electric flows. Okay, yes, now let me elaborate more on it. Okay, so electric flows, electric flows is what? Is the electric flow is the product of electric field passing through a given area, then cos theta. Okay, so this is the formula of what? This is the formula of electric flows. Now the former one I gave you guys is still correct. Okay, yes, okay, it's still very correct. Okay, yes. Now let's go back, let's go to these diagrams you see in the board here. Okay, now before I elaborate more on these things, now if you look at this first diagram, there's what we call normal line. Okay, normal line is that line that is that vertical line. Okay, normal line is a perpendicular line, is a line that is perpendicular to the surface. Okay, look at it. Look, this is surface, right? This is surface. So if you look at normal line is what? That line that was the normal line is usually perpendicular to the surface. Okay, so I want you guys to take note of this. This is normal line. Okay, then you see this other line here. This line known as surface line, or you can say line parallel to the surface. Okay, yes. So for example, let's say I draw something like, let's say this is a shape. Okay, let's say now this line here is known as what? Is a normal line, like, right? While line that is parallel to the surface is known as what? Surface line, right? Yes. So take note of this, very important. So this is a normal line, right? While this is what? Is a line that is what? Parallel to the surface, right? Yes. Now let's start now. Now under this category 1, there are 3 cases. Okay, there are 3 cases. We can call this one case 1. Okay, call this one case 1. We can call this one case 2. Then call this other one case 3. Okay, yes. Now under case 1, when this, please follow me. Okay, now under case 1, when the electric field, remember this line is what? Is a normal line, right? A line that is what? Perpendicular to the surface, right? While surface line is the line that's what? Parallel to the surface, right? This is the surface. Okay, the line that's perpendicular to the surface, or that vertical line is known as a normal line. Okay, yes. Now let me clean this part. Okay, so now on that case 1, very important. Now when the electric field, please take note. When the electric field, I'm coming. Let me write it here. Okay, now when the electric field, is parallel, or when the electric field is parallel to the normal. It's parallel to normal. This is very important though. When the electric field is parallel to normal, what will be electric flux? Will it be maximum or will it be minimum? Okay, when the electric field, this is case one. Okay, when the electric field is parallel to the normal, okay, that is normal line, right? Now this is normal, this is normal line, right? Yes, why this one is surface, right? So let's do it now. When the electric field, remember, okay, let's say this is normal. Now let's do this normal line. Okay, normal line. All right, so this is normal line. Now when the electric field is what is parallel, or when the electric field is along the normal. Okay, so when the electric field, this is the electric field. Now, when the electric field is parallel to the normal, this is normal line, right? It's parallel, right? When the electric field is parallel to normal, what happens? The electric field, what about the surface? The electric field, okay, let me continue. When the electric field is what? Is parallel to what? To the normal, right? Look at it. The electric field is parallel to normal, right? It's parallel to normal. Then what about the surface? If the electric field is parallel to the normal, what will happen to the surface, to the this is surface, right? To the surface line, or the line parallel to the surface. Now, what will happen to the surface? You find out that when the electric field is parallel to the normal, it is perpendicular to the surface, right? Yes. Now let's say this electric field. Now this is electric field. Electric field is what is along the normal line, right? Or is, you can say it is parallel to the normal, right? Yes. If the electric field is parallel to the normal, what about to the this line that is parallel to the surface? It will be what? It will be perpendicular, right? Remember, this is perpendicular line. This is perpendicular, right? At right angle. So let's say this is surface. Let's say this is surface line, and this is what this is electric field. The electric field is what? The electric field is what is perpendicular to the what? To the surface, right? Yes. And it is what? It is parallel to what? This is normal, right? It's parallel to what? To the normal, and is what? Perpendicular to what? To the surface. So under case one, when the electric field is parallel to the normal and perpendicular, at times they will not tell you it's perpendicular to the surface. Okay, I'll just follow me. When the electric field is parallel to the normal, since it's parallel to normal, therefore it is perpendicular to what? It's perpendicular to the surface line, right? Yes. So when the electric field is parallel to the normal, I can put bracket open. That is perpendicular to what? Perpendicular to what? To the surface line, right? To the surface line, right? Yes. So now under case one, when the electric field is what? Is parallel to the normal, what will be the electric flux? Now remember, since it is parallel to the normal, okay, this is normal, right? This is normal. Since the electric field is what? Is parallel to the normal, is there any angle here? No. Since it's parallel to the normal, the angle is zero, right? Yes. Since it's parallel to the normal, the angle between the electric field and the normal line is what? Is zero, right? So under case one, when the electric field is very important, when the electric field is parallel to the when the electric field is parallel to the normal, the angle between them is what? The angle is what? Zero, right? Now let's do it. Cos zero is what? Let's do it. Cos zero is 1, right? Cos 0 is 1. So everything here will be what? Everything here will be 1, right? Times 1. Therefore, electric flux will be equals to what? EA times 1, which should give us what? Which should give us EA, right? Therefore, electric flux is equals to what? Electric field times what? Area. So that's to tell you that, please, this is very important. So that's to tell you that this is an exam-based question. So that's to tell you that electric flux is, so this is maximum, right? Electric flux is maximum when the electric field is what? Is parallel to the normal. Okay, this is very important. So this is formula for maximum electric flux. Electric flux is maximum. This is very important. An exam-based question. When the electric field is what? Is parallel to the normal. Okay, or perpendicular towards the surface. So they can answer. They will say, at one condition is the electric flux maximum. They might not say parallel to the surface. They might say perpendicular. I mean, they might not say parallel to the normal. They might say perpendicular to the surface. That would be the answer, right? Yes. So electric flux is maximum when the electric field is parallel to the normal. It's parallel to the normal and what or and perpendicular to the surface, right? Yes, so that is under case one when the electric field is what is parallel to the normal. Okay, now let's move to the next case two. Okay, let me clean it. Okay, so let me clean this part. Now, under case two, when now under case two, when the electric this one this is not the opposite of this first one. Okay, when the electric field when the electric field is perpendicular to the normal, is perpendicular to the normal line, okay, to the normal. Okay, so now remember this line is what? This line is what is a normal line, right? I told you guys, normal line is a line, it's a vertical line, right? Or you can say a line that is perpendicular to this what to the surface, right? Yes. Now, why this one is what is the surface line, right? Or you can say the line parallel to the surface. Okay. So now, in this case too, when the electric field is what is perpendicular to the normal, that means that the electric field, that is when, let me just clean this third case first. Okay, so now this is the normal, right? Yes. So in this second case, when the electric field is what? When the electric field is what? Is perpendicular to what? To the normal. Right? This is the normal, right? The electric field is what is perpendicular to what? To the normal. Right? And at the same time, it is what? It is parallel to what? It's parallel to the surface. So you can say when the electric field is perpendicular to the normal, that is what? Parallel to the surface, right? Parallel to the surface. Parallel to the surface. Right? So look at it. This is case two. When the electric field is what? The electric field is what? The electric field is what? Is perpendicular. This is perpendicular, right? Yes, this is perpendicular. Why this one is parallel? Right? Parallel, right? Okay, perpendicular. Now look at it. This is normal, right? This is normal. Why this is the electric field? The electric field is what? Is perpendicular. The electric field is perpendicular to what? To the normal, right? Yes. So when the electric field is perpendicular to the normal, now when you say some things are perpendicular, the angle between them is what? Is 90, right? That is at right angle. Right angle is 90 degree, right? So in case two, when the electric field is what is perpendicular to what? To the normal. This is the normal. So electric field is what is perpendicular to the normal. The angle between them is 90, right? So let's do it. Electric flux what will be the electric flux? Electric in that given area, the electric flux will be equal to what? Electric field times the area, then cos. Now the angle between them is 90, right? Cos 90. Okay, now cos 90 is what? Cos 90 is 0, right? So let me check. Yeah, it's 0. Cos 90. Cos 90 is 0. So cos 90, if cos 90 is 0, yeah, okay, so times 0. So E8 times 0 will still give us 0. Therefore, the electric flux is what is minimal. Okay, so the electric flux is minimal. So if they ask you at what condition will the electric field be minimal? So now what am I saying? When at what condition will the electric flux be minimal? Electric flux is minimal when the electric field is perpendicular to what? To the normal of that to the norm. It's perpendicular to what? This is perpendicular to what? To the normal, or you can say it's parallel to the surface, right? Yes. Now the last category. Okay, so the last case. Okay, so let me clean this one. The last case, which is case 3. All right. So so this is the object. This is the surface. Okay. So we all know that this is the normal line, right? So this one is what? The line parallel to the surface, right? Now, now in this case, when the electric field is what? When the electric field is at an angle, okay? When the electric field is at an angle, okay? So when the electric field is at an angle, okay, at a particular angle, that is the electric field is not parallel, it's not 99, it's just declined at an angle. When electric field is declined at an angle, the electric flux will be what? The electric flux will be equals to the electric field times the area, then cos the angle, right? Yes. So which is this very first formula, okay? Yes. So you can find out, you can see that electric flux generally. What is electric flux? I think guys, the electric flux is what is the product of electric field passing through a given area. So you can from this scenario you can find out that electric flux is usually what? Is usually EA. That is when it's maximum, right? Yes. Then it can also be EA cos theta when it's not and when the electric field is at an angle, right? So that's why I tell you guys that's why I told you guys earlier that this formula is correct, this other formula is correct as well. So in summary, electric flux is maximum when the electric field is what is parallel to the what to the normal. It is minimal, that means that it is zero when the electric field is what is perpendicular to the normal. Then it is electric flux is equals to EA cos theta when the electric field is what is at an angle to the is at what is at an angle. Okay, so that is just it. Okay, yes. Now let's move to this second category. This second category, if you don't understand this first category, and I know that you guys understand it perfectly. Okay, but let me still do the second category. Let me use this other. Let me just show you guys second category. Okay, second category is still exactly the same thing. Okay, so but just different illustration. Now we can call this one case 1, case 2, case 3. Now we can call this if you look at this n is what? This n is the normal vector. You can or that the one will refer to the normal line, right? Okay, so this is the normal. Okay, this is the normal. Okay, now you look, this is case 1. All right, so this is case 1. This one will be what? Case 2. Why this one will be what? Case 3, right? Case 3. Okay, remember this line you see here is what? The electric field. Okay, electric field, okay, electric field, right? Yes. Now if you look at this very case 1, this is the normal, this is the electric field, right? What now? What is happening in this first case? Now in this first case, find out that the normal is parallel to what? To the electric field. This is the electric field, right? This is electric field, this is normal and the electric field are all parallel. So that is the very first case that happened that time. So when the electric field is parallel to the electric field is parallel to the normal, the angle between them is what? The angle between them is 0, right? Yes. Therefore, cos 0 will give us 1. Therefore, electric flux will be maximum, right? Because to EA. That is exactly what we did earlier. Then the next scenario. Look at this scenario. This is the normal, right? This is the normal line. This is the normal. Then this is the electric field. Now, this next scenario, find out that the normal is perpendicular to the electric field, right? Look at it. This is the normal, right? Then this is the what? Electric field. In this second category, find out that the normal is what? Perpendicular toward the electric field, right? Therefore, when it's perpendicular, that is 90 degrees, right? And cos 90, okay. Cos 90 will give us what? Will give us 0. 0 times EA will still give us 0, right? So the electric flux is minimal in this second case. Then last case, look at this. In this last case, find out that this is normal, right? This is the normal. Then this is the electric field, right? This is the electric field. The electric field. This is the normal. Then if you look at it, the normal is what? Is at an angle to what? Is at an angle to the what? To the electric field, right? So when it's at an angle to the electric field, the electric flux will be equal to EA cos that particular angle. Simple. So that is just it. Okay, so that is for the first category, then the second category. So you can use any of them. Okay, but we advise you use the first category. Okay, yes. So that's just it. Okay, now let's move to the next part, which is Gauss law. Okay, so move to Gauss law. Now, what does Gauss law? Gauss law is a particular law, right? It's a law. Now, Gauss law, what does it do? Gauss law state that the total electric flux. Okay. So the Gauss law state that the total electric flux passing through a closed surface. Okay, passing through a closed surface, or you can call it a Gaussian surface. Okay, so Gauss law says that the total electric flux passing through a closed, this is total electric flux. Okay, this is the total electric flux passing through a closed surface equals the charge enclosed. Okay, equals the charge enclosed divided by permittivity of free space. Okay, yes. So if you don't know permittivity of free space, I will advise you to go and watch our very first class, that is electrostatic. Okay, so this is Gauss law. Okay, so what does Gauss law state? Gauss law state that the Gauss law state that come on, let me draw it well. This is electric flux, right? Yes. Now, what does Gauss law say that the total electric flux passing through a closed surface. Now, that closed surface can be regarded as what a Gaussian surface. Okay. Yes. Okay. So now, Gauss law says that the total electric flux passing through a closed surface usually equals the charge enclosed. Very important. The charge enclosed by that surface divided by what? Permittivity of free space. Remember, permittivity, E naught, which is permittivity of free space. So you can say permittivity of air. Okay, permittivity of free space. Now, this value, we have given guys the value before in our previous class, is equals to what? 8.854 times 10 raised by minus 12. Okay, so this is Gauss law. Okay, so Gauss law is electric flux equals to what? Charge enclosed over E naught. Okay, now let me go deeper. Okay, now let's say this is a Gaussian surface. Okay, this is a Gaussian surface. Now let's say this is a charge. So a Gaussian surface is a closed surface. Okay, a closed surface. So what is Gauss law? Gauss law telling us? Gauss law telling us that the total electric field. Okay, I mean the total electric flux. Total electric flux. Okay, coming. Total electric flux passing through a given passing through a Gaussian surface. This is a Gaussian surface, a closed symmetrical surface. Okay, this is a Gaussian surface. Okay, so this now the total electric flux passing through the Gaussian surface usually equals to what? This is a charge, right? What does this surface do to the charge? The surface enclose the charge, right? So that's why it's called charge enclosed. So the electric flux equals to what? The total electric flux equals to what? This is a charge that is enclosed, right? A positive charge on that matter. Okay. So the total electric flux passing through a Gaussian surface really equals to what? The charge. The charge that is enclosed, right? So the entire space enclosed. Okay. Enclosed divided by what? Permittivity of free space. So this is the formula for what? Gauss law. Okay, now let's go deeper. All right. So so let's go deeper. Now remember, what is electric flux? Electric flux is what? Is equals to electric field times area. Right. So in the place of this, I can put what? I can put E is equals to what? Charge enclosed divided by what? Permittivity of free space. Right. Yes. Now remember, we all know that from electrostatics or when we know that electric field is what? Electric field is equals to what? KQ over what? R square, right? So in the place of E, we put KQ over R square. So KQ over what? R square, then times area is equals to what? The charge enclosed divided by what? E naught, right? Yes. So if we, right? So, okay. So that is just it. Okay, so we can keep on coming. Okay, yes, we can keep on breaking it down little by little. I think this one will cancel this. Then yes. So but just take note of this. Okay, we will expand later when we get to this place. We will expand. All right. So that is just it. Okay, so found that so now this electric field times area is equals to charge all over E naught, right? So we want to make E stand alone. Therefore, electric field can also be equals to what? Can also be equals to charge enclosed divided by what? Divided by area times E naught, right? Yes. So that is just it. Okay. Yeah. So that is just it. All right. So there are okay. That is just that there are a lot. Okay. So now, if you don't want to just waste your time in a particular question, let's say in an exam-based question, let's say calculate for the electric flux, right? They say calculate for this is very important. Okay. So now, let's say in an exam-based question, they say calculate for electric flux. For example, they give you electric field, they give you the area of the Gaussian surface, they give you other stuff, they give you radius and all, and they give you charge. This is very important. They give you charge. Just forget about everything. Just put the charge divided by what you know to get your answer. No matter what they give you. I don't even understand. Yes. let me break it down. Let's say, for example, okay, okay. Now, all right. So, like, if the let's say, for example, they say calculate for electric flows, right? They say calculate for electric flows. They give you now. If we now before then, let's continue now. Before I go for let's now. If we expand this, okay, before I forget, if we expand, remember E is what electric field, right? Remember electric field is what KQ over what R square, right? Then times what A, right? Yes. Now, in some particular question, they can say, I'm coming. So therefore, electric flow is equals to KQ times A over what R square, right? Yes. So now they can say calculate for electric flows. For example, they'll give you area, give you radius, give you this, give you that. You don't need to stress yourself. Remember, electric flow is equal to charge enclosed over divided by what? Divided by E naught, right? So just put your charge there. Let's say the charge is 2. You put your charge divided by what? E naught. Remember, what is E naught? I told you guys permittivity of free space, right? Which is what? 8.854 times 10 to the power minus 12. Okay? If you just do this, you get your answer. Okay? No matter the values they give you, as long as they give you charge. Okay? It's not as if if you don't use this one, you not get electric flow, so you get it, but to be fast, once they give you charge, divide it by what E naught, you get your answer. Okay? So in summary to what we have been doing earlier, Gauss law states that the total electric flows passing through a closed surface is equals the charge enclosed by the surface divided by what permittivity of what free space. Okay, yes. So we all know that electric flows is equals to what EA, right? Which is electric field times area equals to what charge enclosed over what over E naught. So that is just it. Okay, yes. So there are a lot of things. All right. Now let's move to the next part. Application of what of Gauss law. Okay, application of Gauss law. Okay, now there are three applications of Gauss law. Okay, yes, there are three applications of Gauss law. One, the very first application is when a charge, when a point charge, okay, that is a single charge. When a point charge is enclosed by a sphere. That is for the first application. When a point charge, okay, when a point charge is enclosed by, this is the first application by what? That is the first application by a sphere. Okay, by a sphere. Okay, yes, when a point charge is enclosed by a sphere. Okay, so let's say this is a sphere. Now this is the point charge. Okay, the point charge is what? Is enclosed by this sphere. Don't mind my drawing. Okay, so okay. So well, they'll ask you what is the formula we are going to use to calculate for the electric flows. Okay, now before I continue, just take note that for an outward, remember electric positive charge give off what the electric field is usually outward, right? Yes, so the electric field is usually outward, then with the area gives you the electric flows, right? Remember, electric flow is equal to what? Electric field times what? Area, right? Yes. So now, okay, so when that is application one, when a point charge is enclosed by what? By a sphere. Okay, when enclosed by a sphere, so it can be a point, can be a positive charge, can be a negative charge. If it's a negative charge, it might be something like this, right? It might be something like this, right? Yeah, something like this, right? So let's use positive. Okay, let's use positive. All right. So when okay, when a point charge is enclosed by what? By a sphere. So this does calculate for the now what if the house was to calculate for the electric flows? How are we going to do it? It's very easy. Okay, yes, the formula. Let me give you guys the formula we're going to use. Okay, yes, remember that very first thing I told you guys. You guys, when they give you charge, when they give charge, don't just stress yourself. Divide the charge divided by E naught, you get your answer. Okay, so but let's continue. Okay, when a point charge is enclosed by what? By a sphere. Now what will be the formula we are going to use to calculate for the the electric flux. Remember from Gauss law, this is an application of Gauss law. Gauss law, we state that charge enclosed divided by what? Divided by E naught, right? Yes, divided by permittivity of free space. Okay, yes. So okay, now we all know that from electric flows is what? You know that electric flows is what? Electric flows, remember, what is electric flows? The product of electric field passing through a given area, right? So EA, right? So in the place of flows, we put what? EA, right? Equals to charge enclosed divided by what? E naught. Now, since this is a sphere, where is the area? Now where is the area of the sphere? The area of the sphere is what? Is 4 pi r square, right? It's 4 pi r square. So in the place of um um area, we'll put what? 4 pi r square. So E 4 pi r square is equals to the charge enclosed divided by what? E naught. So if I have to continue further, okay. So if I have to continue further, want to and now let me what is the essence of this application of Gauss law? It's used to we can use in this application is used to determine the electric field produced by what? By a point charge when it's close by a sphere. By a sphere, okay? So not the electric flux, okay? So that is just it, okay? Now let me recapitulate what I'm saying. Okay, so the very first application is when a point charge is enclosed by a sphere. So for example, they'll say, okay, calculate for, it's not the electric flux. Now they'll say, okay, calculate for the electric field when a point charge is enclosed by a sphere. Okay, yes. So how we're going to do it? We use Gauss law. Okay, Gauss law, we state that electric flux is equals to charge over what? E naught, right? But remember, electric flux is equals to what? EA. We want to look for the electric field produced by what? By the charge enclosed by what? By that sphere, right? So that's how I'm using Gauss law. EA is equals to charge over E naught, right? So area, which is what? The A, which is the area of the what? Of the sphere. Area of the sphere is known as 4 pi r square, right? So we want to make east and north. So what are we going to do? Divide both sides by this one, right? So in the end of the day, we have something like this. Electric field will be equals to what? The charge enclosed divided by what? Divided by 4 pi 4 pi r square E naught. Okay, so this is the formula to calculate for the electric field when a point charge is enclosed by what? When a point charge is enclosed by a sphere. Okay, so this is the very first application of what? Gauss law. So electric field will be equals to what? Charge over what? 4 pi r square E naught. So that's just it, okay? Now let's move to the next application. Now let's continue with the next application, okay? So the very first application is when a point charge is enclosed by a sphere. What is the electric field? How to determine the electric field of that point charge? Okay, so what will be the electric field of that point charge when it's enclosed by a sphere? We use what? Gauss law, right? Yes. Now the next application, okay? Now for the next application, taking on this first formula, okay? So for the next application, when yes, the next application when an infinite line of when an infinite line of charge is enclosed, okay, is enclosed by a Gaussian surface, by a Gaussian okay, let me spell, okay, by a Gaussian surface, okay, by a Gaussian surface, okay. So the first application was for a point charge, right? How are we going to determine the electric field produced by that point charge when it is enclosed by a sphere? So this is the formula, right? I've given you guys. Now what about for an infinite line of charge? What is an infinite line of charge? Something like this, okay? A linear object that has distribution of charge around along it, okay? So now how are we going to determine the electric field produced by this how are we going to determine the electric field produced by this infinite line of charge. Okay, infinite line of what? Charge. Okay, so we are going to use what? Gauss law, right? Yeah, we are going to use Gauss law to determine the electric field produced by an infinite line of charge. Okay, so this is one of the this is an application of what? Gauss law, right? Yes. So how are we going to do it? Remember, for Gauss law, the charge need to be what? Need to be enclosed in a surface first. Now remember, Gauss law said that the electric flux is equals to what? Electric flux is only equals to the charge enclosed, right? Divided by what? Permittivity of free space. So this charge need to be what? Need to be enclosed. Which Gaussian surface are we going to use? We use what? We use a cylinder. Okay, we use what? A cylinder. All right. So use a cylinder. Okay, so the cylinder act as what? Act as what? As a Gaussian surface, right? Yes, the charge need to be enclosed. Okay, so this okay the cylinder act as a Gaussian surface, right? Yes. So if at the time the electric field produced by an infinite line of charge enclosed by a Gaussian surface such as what? A cylinder. Okay, so what is the formula we are going to use to calculate for the electric field? It's very easy. Okay, so we are going to make use of Gauss law, right? Yes, we're going to make use of Gauss law, right? And when it's God of Gauss law state, Gauss law state that the electric flux is equals to charge enclosed, right? These are charges that are enclosed. The charges are enclosed by what? By this cylinder, right? Yes, charge enclosed over what? Over E naught, right? Permittivity of free space, right? Yes. Now remember, what is flux? Electric flux. Electric flux is what? Is what? Electric field times what? Area, right? It's equals to charge enclosed divided by what? This E naught, right? Yes. Now what is area? This area is what? Is area of what? Is the area of the cylinder. Now what is the area of the cylinder? It's very easy. The area of the cylinder is what? Is 2 pi r L. I'm not mistaken, okay? This formula for what? This is the area for what? Of a cylinder, 2 pi r L. So in the place of A, we put what? 2 pi r L, right? So electric field now be what? E times what? Area is what? 2 pi r L, right? It's equals to charge over what? E naught. So let's come to this place. So okay. So okay, E naught. Okay, so if we want to make E standalone, so divide both sides by 2 pi r L, right? So now before I continue, thank God I remember. Okay, so before I continue, let's just pause here and go back to this place. So remember now, this is what? This is an infinite line of charge, right? An infinite line of charge. Now there's one quantity that tells us the amount of charge along a particular length. Let me that quantity is known as what? I've told you guys in my previous class, linear charge density, right? Linear charge density. So this is the value, this is the symbol. Linear charge density is what? Is charge, so is an amount of charge divided by what? Divided per unit length, right? Amount of charge. Let's say this is a linear object, right? It has charges distributed along it. So the linear charge density is what? Is because I'm giving you earlier in our previous class, charge per what? Charge per length. Let's say this the length of this wire, or yeah, this object is, let's say this length is 10, for example. Then the amount of charge distributed along this length is, let's say, 5. Therefore the linear charge density will be 5/10, right? Yes. So let's not forget about linear charge density. This is very important. Remember, linear charge density, since now linear charge density. So if we make charge stand alone cross multiply, charge will be equals to what? Will be equals to linear charge density times what? Times length, right? Yes. So in the place of charge, I'll put what? Linear charge density times what? Times length, right? Yes. So very important. So this is for an infinite line of charge. For an infinite line of charge, it is commonly known as what? Linear charge density, right? Yes. So charge is equals to what? Is equals to linear charge density times what? Times length, right? So remember, E, then area of a cylinder is what? Is 2 pi r L, right? Is equals to Then charge, right, over what? E naught, which is permittivity of free space. Now, what is charge? Charge is what? Is linear charge density times what? Times length. So linear charge density times length, right? Yes, if we continue, this L will cancel this L, right? So we'll now be left with electric field times 2 pi r equals to what? Equals to linear charge density over what? Over E naught, right? So if we continue further, I want to make electric field time known. That was said by what? 2 pi r, right? So that was said by 2 pi r. I know. We now have something like this. We now have something like this. If we divide both sides by 2 pi r, okay, 2 pi r, we have something like this. Electric field now be equals to what? Now be equals to linear charge density over what? 2 pi r E naught, right? Yes, or you can say equals to uh, linear charge density over 2 pi E naught r. This is the same thing, okay? So that is just it. So let me the formula. So when for an infinite, we can look for the electric field. So we can look for electric field of an infinite line of charge that is enclosed in a Gaussian surface such as a cylinder. The formula to look for the electric field is what? Is equals to linear charge density over what? 2 pi E naught r. Okay, yes. So it's very important. Okay. So it was very, very important. So this is second formula. Okay, take note. That's for an infinite line of charge. This one is what? Linear what? Linear charge density. Okay, linear charge density. Okay, then application. The last application. The last application. Okay, the last application of Gauss law is when an infinite when an infinite plane of charge is enclosed by Gaussian surface. Okay, so for a plane of charge, this is a plane of charge. Okay, so let me see how I can do it fast. All right. Okay, coming. All right. Okay. So now this is a plane of charge, right? A planar object. This is a plane of charge. So now, if I determine the electric field produced by this infinite plane of charge, which from now we're going to do, how we're going to get how we're going to calculate for electric field. It's very easy. We use Gauss law, right? Yes. What is Gauss law? Gauss law. We say that electric flows is equals to charge enclosed over what? Over E naught, right? Yes. Now look at it. These are multiples. These are collections of charges, right? Yes. And to get the electric field, we need to use Gauss law, right? Use Gauss law. Now, if we have to use Gauss law, we need to enclose these charges in a Gaussian surface, in a surface, right? Yes. So which surface are we going to use? Okay, so we are going to use a cylinder as well. Okay, so let's say use a cylinder. I'm coming. Let's say use a cylinder. Okay, so this is one end of the cylinder, this is the other end. So this is the part. Okay, so let me see. Let's say for example, so this is the part of the charge enclosed by what? By the cylinder, right? Yeah, this is part enclosed by cylinder. It can also be something like this. On that scenario, I'm coming. Also be something like this. Okay. All right. Can also use a cylinder like this. Okay. So something like this as well. So there will just be particular. Okay. So now this electric field produced by what? The charges, right? If you look at it very well, you find out that if you find out that the electric field um, usually comes out from the two end of this cylinder, right? Yes, that is two electric field. I don't understand. So the yeah. Now let's continue. Two electric field, right? Now remember, what does Gauss law say? The Gauss law says that electric flows usually equals to what? The charge enclosed divided by what? Divided by charge enclosed divided by permittivity of free space, right? Yes. Now Where's electric flux? Electric flux is equals to what? EA, right? Yes. So in place of flux, we put what? Electric field times A is equals to charge enclosed divided by what? A naught, right? If you look at it very well, there are what? There are two electric field, right? So the total electric field here is what? Is 2. So total electric field here is what? The total electric field. Total electric field is what? Is 2, right? So we can call this one E1, E2. So E1 plus E2, right? So total electric field boy is is 2E, two electric field, right? Yes. So in this place, we put what? We put two electric. The electric field is what? Is 2, right? There are two electric field, right? Yes. So okay. Okay, we are okay. So I'm coming. We arrive with something like this. 2EA is equals to charge over what? Over E naught. Now remember, we are dealing with what? We are dealing with an infinite plane of charge. Now in an infinite plane of charge, there's what we call surface charge density. Okay, there's what we call surface charge density. Now what is surface charge density? Surface charge density is the amount of charges distributed in per unit area. Amount of charge per unit what? Area. Okay. So let's say this is a particular surface, right? This is a particular surface. Okay. Now surface charge this I've taught you guys that in our previous class. This is surface this symbol of surface charge density. Okay, surface charge density usually equals to what? The amount of charge in what? In this occupying what? Occupying this area, right? Per unit area, right? Yes. So remember, in an infinite line of charge, that is for a linear object, we make use of what? For a linear object, we make use of linear charge density, right? Which is with linear charge density, which is equals to what? The amount of charge occupying what? This length, right? Yes. So for a plane, for a surface, we make use of what? Surface charge density, right? What is surface charge density? Surface charge density is the amount of charge occupying what? Occupying particular area, or you can say charge per area. Okay, so pi equals to I mean sigma, which is this symbol is sigma. Okay, so surface charge density is equals to charge over what? Area, right? Yes. So let's not forget about this part. We are not done yet. Okay, so if we make charge stand alone, charge will be equals to what? Surface charge density times what? Times area, right? Yes. So let's go back to this formula now. Gauss law said that electric flux equals to charge enclosed over what? E naught. Now for an infinite plane of charge that is enclosed by what? That is enclosed by a cylinder. Find out that there are two electric fields, right? Yes. So two electric fields. If we had this, we have what? 2E, right? So 2EA is equals to charge over what? E naught. Now what is charge? Charge is what? Surface charge density times what? Area. So in the place of charge, we put what? We'll put surface charge density times what? Times area, right? Yes. So this, if I found that this A will cancel this A, we'll left with 2E is equals to surface charge density over what? E naught, right? We have both side by 2. Okay. So I'll cancel this. Therefore, let me clean. Therefore, electric field will be equals to what? Surface charge density over what? 2 permittivity of free space. So this is the third formula. Okay. Yes. So that is it. That is all about application of Gauss law. You know, in everything. Okay. Don't stress yourself deriving. You don't stress yourself deriving just on the formula. So for a charge that is enclosed by a sphere, okay, for a charge is enclosed by a sphere, to calculate the to calculate the electric field produced by that charge, we make use of Gauss law, right? We enclose the charge using a sphere because Gauss law will involve a Gaussian surface, right? A closed surface enclosing the charge, right? So we know that electric flux is what? Is EA, right? It's equals to charge over E naught. Now A, okay, divide both sides by A, we have something like this. Electric field now because what? Charge over what? AE naught, right? Now what is the area of a sphere? The area of a sphere is 4 pi r square. Therefore, electric field due to when a charge is enclosed by a sphere usually equals to what? 4 pi E naught r square. So this is for what? This is for when a point charge is enclosed by a sphere. This one is for what? The electric formula you can look for the electric field of an infinite line of charge. Okay, while this last one is formula to calculate for, which is electric field is equals to surface charge density over what? Two of what? Two um permittivity of free space, right? So this one is for what? For an Yeah, this formula to calculate for the electric field of for an infinite plane of charge, right? I've explained that down earlier. So take note of this, take note of this, take note of this. We are good to go. Okay, so this is what? This is linear charge density. This is surface charge density. Now, what is surface charge density? Surface charge density is what? Is charge over what? Area. Linear charge density is what? Is charge over what? Length. So just that, just it. Okay, and one more thing I need to tell you guys. Okay, still important. Okay, so one more thing I need to tell you guys is I think you guys know this symbol now. This is micro, and what is the micro? Micro is what? 10 raised by minus 6. This is milli. Milli is what? 10 raised by what? Minus 3. When you see P is pico, it's 10 raised by minus 12. Then there's still one value that looks like this. I think there is Armstrong. I don't think I pronounce it well. It's 10 raised by 1 minus 10. Okay, yes, if I'm not mistaken. Okay, so just think on these values. Okay, I think you guys know it. This one is macro, milli, pico, Armstrong or so. So macro is 10 raised by minus 6, milli is 10 raised by minus 3, pico is 10 raised by minus 12, Armstrong is 10 raised by what? Minus 10. Okay, so that's just it. Now let's move to what? To question and answer.